Uh, I don't know, for some reason it got disconnected. So we are back live. Uh, So I don't know why we got disconnected. So we are back online again. So as I mentioned that it it cannot just drop down to zero. You got to give it a little space for the frequency response to come down, and this is called the transition band. And then once it is in the stop band, again it cannot just go back to zero, so the magnitude would go up and down, up and down, up and down like this. Basically you allow some ripples, and these are usually we denote this as delta 2, and these are called stop band ripples. Stop band ripples. So if you look at the frequency response even in MATLAB, you will realize that MATLAB has divided this region into three parts. So MATLAB has divided this region into three parts. One part is called the pass band. This part is called the pass band, where you want your frequencies to pass. Okay, so your frequencies will live, and you allow this to live here. Okay, this is your pass band. Then is your, this is called transition band. So you let your frequencies to live, or the frequency response to live anywhere here, not any other place but here. So this is the transition band. And the third one, which is here, where we don't want the frequencies to pass, is called the stop band. Okay, and this is the stop band. So you want this to, and this is pi, this is 1. This is your magnitude of the frequency response. This frequency is usually called omega of p. This is called omega of s. This value is usually called delta of 2, and this value above 1 is called 1 plus delta of 1. Okay, so this is called the pass band ripple, and this is called the stop band ripples. Okay, so once you look at this, this is how it looks like. That you are to design a filter. You cannot design an ideal filter, so you got to live with something which is realistic, and something realistic would require you to have a little tolerance. You got to give a little tolerance for the frequency response to live in a pass band, this yellow region, and a little tolerance for the frequency response to live in the transition band, as it cannot just drop down to zero, and a little transition or little space you got to give it to live in the stop band. It cannot remain zero. The frequency response, absolutely there is no way for the frequency response. So and we have seen this. Once you look at this, you will find out that your response will be something like this. Okay, so usually the frequency response would look like this. Okay, it will live, and it will never look like this. This is not possible for a frequency response to look like this. It will look like this. So this is what reality is. So this is real. So we say, okay, we understand this, and the design problem, we need to specify delta 1, we need to specify delta 2, we need to specify omega pass, we need to specify omega s. So these are the things you got to specify once you are designing either an FIR or an IR filter. Okay, so you got to know this, that you got to know all these before you are designing an IIR or an FIR filter. See? So knowing this much, that this is important for us to understand that what is real and what is ideal, and only the real is possible, ideal is not possible. Now we move to the second decision you need to make as a designer. A second decision you need to make as a designer. Should you design an FIR or an IR filter? Okay, it's up to you. You can select a filter, because a filter primarily what it does, it removes unwanted frequencies from your signal, and this is very fundamental of signal processing, digital communication, that you got to remove what is not required, what is noise, and so you got to remove that. So your decision, FIR versus IR. FIR usually will have linear phase, okay, and there are like ways of making this is usually non-linear phase, and we know that. But then there are ways of making it a linear phase as well, like putting an all pass filter, or there are some techniques which helps you to basically have a close to linear phase in the pass band, and you don't worry about the stop band, that how your phase performs in the stop band, because those are the frequencies which you ultimately are going to filter out. This is always stable, so you don't need to worry about its stability. You need to worry about its stability. All the poles must be inside the unit circle. It has usually large order, so this is a compromise. Whether you want more computation, okay, but you don't want to worry about stability, you don't want to worry about the phase, or you want less computation. Usually these are less order, smaller order, or so to say smaller order. Okay, it's up to you whether you want to do this or this. But main problem with this is also it is susceptible to quantization error, and we have seen that susceptible to quantization error, because once you quantize your coefficients, the location of poles will change, and once the location of poles are changing, they'll change your frequency response as well. So here the quantization would affect the response and the stability criteria. Here you usually don't worry too much about the quantization, and so it's your decision to make. And people in many applications, you will find out they have already devised that where to use an IR and where not to use an IR. Okay, so with this we need to know how to design either one of these, how to design an IR filter or an FIR filter. So let's first study how to design an IIR, which is infinite impulse response. How to design an infinite impulse response system, how to do that. So this is interesting that people would not spend their time to find a digital way of designing a digital IR filter. They would not spend, because people have spent their life in finding out ways of designing an IR filter in continuous domain. Okay, there are many mathematicians, electronic engineers, they have spent like their life in designing continuous domain IIR filter, which are implemented using circuits. Okay, passive filters. There used to be courses, passive filter. Okay, in electronics there used to be courses, like you're studying digital signal processing, there used to be a course to learn passive filters. How do you design passive filters? Now, how to use capacitor. Passive means that there is no energy source, so there are only passive electronic elements like capacitor and inductor and resistors that you can use to design an electronic system. So courses where you learn this. So signal processing people are smart. They thought, why to invest our energies in figuring out what people have spent a lot of time in actually designing. So I said, let's not worry about designing IIR filters or systems using digital techniques. Okay, you will hardly find any technique which can digitally design a digital IIR filter. Okay, they play a trick, and the trick is that why not? So the trick is simple. Why not I have this digital my specifications are in digital domain, so discrete time specs. Okay, I have discrete time specifications. So I convert these specifications into continuous time specifications. Interesting. Okay, so I convert from discrete time, like we sample and then we convert them into an analog sample by passing the digital signal through a D2A converter. The signal becomes an analog. So there is kind of a one-to-one relationship between a discrete time and a continuous time system through the process of sampling. Okay, this is easiest to comprehend. If I have something which is in discrete time domain, I can actually create even the specifications which are in continuous time specifications. And now go back to history, go back to these people who have spent a lot of time in designing continuous domain IR filters. So use all the tricks and techniques which people have already developed and design. So this is a design problem. So you design a continuous time filter, which usually is an S domain. A transfer function is HS. You must have studied these in your circuit course. Transfer function is in the Laplace transform, H of S, that converts into a differential equation. Okay, a circuit is nothing but a differential equation, and that's how. And then you can convert it. You can look at its frequency response by putting omega is equal to 0. H omega is the frequency response of the system. So this is the Laplace transform, and Laplace transform has H of S, and its frequency transform is H omega. So you design something which is in continuous time, and then you use the same technique. What if you have something in continuous time? The process of sampling will convert a continuous time signal, or so to say a system, into a discrete time design. So you get what you wanted to have. So this is a smartest thing which people have done, and that will require us to learn all the techniques which are used to design continuous domain IAR systems, which are implemented using circuits, using capacitor, inductors and resistors. So we got to go back to the course, which usually is an electronics course, and learn how to design a continuous time IAR filter. Okay, so there are different techniques, and these techniques are a scientist or an engineer, maybe electronic engineer, named Butterworth. Butterworth has come up with a design, and they must be genius, and I'll tell you why I consider them as genius. They may be, because it's amazing that how they basically design these things. Chebyshev, and the third technique which is given in the book, and there are other techniques as well, but the book covers these three techniques. Elliptic. So the important is not that you learn these techniques, important is you learn the methodology, that how the people like Butterworth and Chebyshev and this is the elliptic, and how could they actually design something given a specifications. And this is really amazing. If you start thinking about it, it's amazing. And how could they come up with an idea of taking a specifications? Okay, it's mind-boggling that how can you, they must be genius, that how could you come up with something which shows like this, because passive filters the frequency response can never go above 1. Okay, it can go 1 and less than 1. So usually it is 1 minus delta 1. Then is the transition, omega pass and omega stop, and then there is delta of 2. So this is how usually the specifications are written for converting. This is a discrete time specification. So this is h exponential j omega, and you convert these specifications into continuous domain specifications. In continuous domain, yes, 1, and this is 1 minus delta of 1. This is capital omega of p, because now it is analog frequency. This is capital of omega of s, and this goes to infinity. Now the frequency does not contain till pi. Analog frequencies can go to infinity, and here the response is h exponential j, h j omega magnitude. Okay, here this is magnitude, and here is the delta of 2. So first of all, the specifications are given like this. You need to convert these specifications like these. So continuous domain specifications. And now your frequency response would be something that is here. Okay. And now just think of a specs which is given like this, and magically somehow coming up to a transfer function h of s, which is like b0 plus b1s plus b2s square divided by 1 plus a1s plus a2s square plus this. Okay, so coming up with a transfer function, taking this drawing and converting it into a mathematical function, and how, and the best possible way, like to meet this curve, to meet these specifications, that its life is only limited to this region, then its life is limited to this region, then its life is limited to this region. How could you convert something which is even not in S domain, which is in omega domain, and converting this thing, the specs, to a system? And then there is a theory that once we have these coefficients, and we know that if it is only first order, then you can design it as an RC circuit. If it is second order, then you need to have an RLC circuit. It will have a resistor, a capacitor, and an inductor. And if you have higher order, then you have more of capacitors and resistors and inductors. So there is, extension to this is, then once you have these coefficients, you need to convert them into actual value of resistors and inductor and capacitors or capacitance. So we are not getting into that, because our only objective is to find a transfer function. So how to find a transfer function? Taking a curve, finding a transfer function. So first see how the Butterworth solved this problem. Butterworth was very smart, and he thought about this, and must have, like, if I get into his shoes, he must be thinking that how can I convert a curve, okay, or a graph into a transfer function like this. Okay, so what Butterworth did was, it said that let me draw this with red color. So this is the passband. So he made his problem a simple problem to solve, because somehow he needs to write this mathematically, this curve mathematically. And the easiest mathematical representation he must have thought about, he must be a good mathematician, that what if it is a monotonically decreasing function of omega? My frequency response is a monotonically decreasing function. Monotonically decreasing means it starts from 1, just keep going down, 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 down. It touches this, which is my omega of pass. And then it sharply drops down to point, which is omega of s. And then it hits and keep going down, down, down till it hits infinity. This is a monotonically decreasing function of omega. Though you can ripple in this region, so you are allowed to ripple here, you are allowed to ripple here, but it said let me not worry about, once I put ripples, then I may not able to easily write a mathematical expression where there are ripples here and ripples here. I take a very simple curve, like as you know, what is x in mathematically, you can draw x like this. So this is your x, okay, and if you do 1 over x, it becomes this. Okay, once it is 0, it goes to infinity. Once you have high value, 1 over x goes to 0. So this is a curve. So this is simple to write, this is simple to write. And how do you write this? Okay, and your x is now omega, which is, this is omega. So he then came up with a way of writing this curve mathematically. Okay, and this is where I say he was a genius, that he could find a simple mathematical expression that can do this, that can dive like this, touch this point, dive like this, touch this points, and at every point its value is less than a value of the function at some smaller values of omega. So this is called monotonically decreasing function of omega. So he could actually come up with a mathematical expression. So he said this mathematical expression is actually j omega square is equal to 1 over 1 plus j omega over j omega c raised to the power 2n. Okay, so he came up with a function like this. What does it mean really? It means that he said if you have a function of x, okay, a function of x that look like this, 1 over 1 plus x over a square. I'm just putting a square now, okay, but he said this could be a 2n, and what n would do I'll tell you in a while. So he said if you plot a function of x like this, so interestingly somehow this is a, so this is a. So what this function would do, that it will start from 1, x is equal to 0, it will be 1, and then it'll come down and sharply drop across a, and then we'll do this. So this is a function which he used, and somehow he could figure out there is a function which could just behave like this, and this is, he said, wow, now I have something, bingo, I have something where I can, if somehow I can now convert it into s. Still the problem is there is an omega in it. How to convert this omega into an s? Still there is, he must have been thinking that how to basically convert this omega into a function of s, because this is a function of omega and somehow you need to convert it into a function of s, and then you figure out the values of capacitor, resistors and inductors. Okay, so he solved one part of the puzzle, one piece of the puzzle, that yes, there is a mathematical function which behave like this, and this is a mathematical function. Okay, but now he needs to solve the second part of the problem, that somehow converting this into a transfer function, that basically gives you an h of s. So how he did that? Let's now see his genius, that how could he basically able to figure out a relationship between hc of j omega and h of s. So he said, I know the magnitude is actually, once you say magnitude square, okay, a magnitude square is if you multiply a function with its conjugate. So this we know from our elementary maths, or the courses you have taken even in your FSC. Maths tells us that the magnitude of complex number, if it's a complex function, magnitude square is this multiplied by its conjugate. He said, okay, I know this much. And then, because we know what is the conjugate, conjugate is you convert j into minus j. He said, okay, conjugate can be written as, wherever there is a j, you change it into minus j. This is what a conjugate is. Okay. Then he said, oh, I also know that s is equal to sigma plus j omega. Now he's now getting from hc of j omega square, he wants to figure out h of s. Okay, so these are the steps. So, and said, wow, so I know s is equal to sigma plus j omega. So, and once I want to go from h of s, that's bullshit. If I put sigma is equal to 0, then it becomes exactly this expression, okay, because s is sigma plus j omega. Put sigma is equal to 0, sigma goes away, then it is j omega raised to the power 2n. So he is still not close, because you don't need h of s and h of minus s, you only need h of s. So he's still struggling. He's saying, okay, I'm close, but still I have something which does not look like this. Number one, does not look like this, and where there are coefficient b0, b1, b2, this. And secondly, I have an h of minus s. So somehow I need to cut this into half. I throw away this part and keep only this part because I want an h of s. Okay, so then he must have been thinking that how can I split this expression, how can I split this expression into two parts in such a way that there is a relationship between the two parts. One is h of s, and if I replace s by minus s, I get the second part. So splitting this is just one piece. And you say, wow, how can I split this into two parts where I keep half of it, and half of it must look similar but must have a minus s in it. Okay, so you must be again thinking, how should I do this, how should I do this? Okay, for example, if I have a function of x square, let's say if it is a function of x and function of minus x, for example, just narrating this, and this is 1 over 1 plus x square, or 1 minus x square, let me see, 1 minus x square, simple. So you say, oh, I think I can split it into two parts, one is 1 minus x and the other one is 1 plus x. This is beautiful because now I have successfully split a function into two parts with this relationship in it, that one part is similar to the other part. Only if I replace x by minus x, I get the other part. So I say f of x could be any one of these two, and I can say this is my f of x and this is of minus f of x, which is 1 over 1 plus x. Okay, so you got to come up with something like this where you first expand this into its factors, expand this function into its factors, and then split them into two parts. Also, he must be thinking about how to expand this into factors, give half of them to h of s and rest half of them to h of minus s in a way that this relationship is not violated. So here comes the third part of it. So he's slowly but surely he's moving towards a solution. Interestingly, moving towards a solution, a discovery. I would say again, as I mentioned, he must be a genius that he thought in these ways. Okay, so he said, look at this. If I have something like this, 1 plus x square, I know I can split it into its roots or its factors. And how do you make factors of this? You say, okay, 1 plus x square is equal to 0. I find out the roots of this function, and then based on the roots, I can factorize this. So say this is x square is equal to minus 1. So it means x is equal to plus minus iota, or plus minus minus 1. So x is equal to plus minus iota. So these are the two roots of 1 plus x square. If you plot them, a root here and a root here. These are the roots of 1 plus x square. Okay, 1 plus x square has a root and there is no real part in it. One is iota or a j, and other one is minus iota. So if I write this as an x minus iota or x plus iota. So this is how you factorize 1 plus x square into two factors x, and once you multiply them together, you are going to get this 1 plus x square. Okay, so you say, wow, means that I know 1 plus x. What if it is 1 plus x cube? Okay, what it is 1 plus x cube? And you have done this in maths. So you have done this in maths, if you remember. It is 1 omega square. There are three roots. Okay, it is one is here, and it is 360 divided by 3. One is at 120, equally placed at 1 and omega square, something like this. Okay, so there are three roots, and these are called roots of unity. And this in generic, it is called nth root of unity. If you go back, and at that point, you must not have considered that you are going to use it, somewhere. But in maths, I remember that you learn about nth root of unity. Nth root of unity means that if you have an expression like this, 1 plus x raised to the power n, and you are asked to find out its root. So you put this is equal to 0. You have x of n is equal to minus 1. You have x is equal to minus 1 raised to the power 1 over n. So there has to be n roots. Okay? There has to be n roots. And how do you calculate n roots? They are going to be equally placed on the unit circle. Equally placed. If they are 4, maybe like this. If they are 5, they are 6 or 10 or 12. They are going to be equally placed on the unit circle. So people must be good in mathematics. So if you look at now this expression, and you want to find out 2n roots of unity. It is 2n roots of unity. Okay? Because it's an expression like this, you say, wow, I think I can figure this out. All the roots, because I need to find out roots as I did here. I first find out roots, then I split them into factors, and once I have factors, I give half of them to this and half of them to f of minus x. So I am precisely going to do the same. I am going to split. First I will figure out 2n roots of this expression. I will give half of these to h of s and rest half of these to h of minus s. Okay, let me just recap, because this is the genius of Butterworth, and he could figure out a graphical expression which could live in this area, which is the allow area, not getting into the forbidden. So rest is the forbidden areas. Live its life in this region, and it's a nice mathematical expression like this. So he said, wow, I have now a mathematical expression, but this is for magnitude square. The second one, what to do with the magnitude square? You said, yes, let's have magnitude is this into its conjugate, and conjugate is minus, but I want an expression in S, so I know S has a relationship with omega, which is sigma plus j omega, and once you put sigma is equal to 0, you want to get back to this expression, so he replaced h j omega with S, h of minus j omega with minus S, and so in this expression he has S over 2j omega, see this. And then we are learning about something which you basically learned in your mathematics courses, nth root of unity. And nth root of unity, I just explained that if you have complex roots, depending upon how many of these are there, if they are only 2, so you have these are the 2 roots of unity. If they are 3, there will be 3, there may be 4, there may be 5, and they will be equally spaced on the unit circle. So in maths we learn about nth root of unity. So this expression appears to me the same expression where I need to learn about nth root of this 1 plus s over j omega c raised to the power 2n is to be put equal to 0. Okay, so I am now what I'm trying to do is I am finding out 2n roots of this. Okay, 2n roots of this. So put 0, so this becomes s j omega c raised to the power 2n is equal to minus 1, of course, right? And then you take 1 over 2n, so it becomes s over j omega c is equal to minus 1 over 1 over 2n. So this minus 1 over 2n, as was here, 1 plus xn is equal to 1, xn is equal to minus 1, x is equal to minus 1 is equal to 1 over n, has nth root of unity, means a circle which is magnitude is 1, and there are going to be n roots. So similarly here, but this is not s, there is a j omega c here. So you say, wow, I need to bring the j omega c on the other side. So you say j omega c minus 1 over 2n, and j is actually can be written as exponential j pi over 2. So instead of circle 1, it is going to have a circle with radius omega c, because it's multiplied by omega c. So once you draw this, interesting, there is a circle omega c and pi by 2. Starting from here, you are going to have 2n roots of unity. So you say 360 degrees divided by, let's say n is equal to 2. So 4. 360 divided by 4. What is 360 divided by 4? 90. So you are going to have 4 roots which are going to be 90 degrees apart. First you start, so they are going to be, first is going to have this, so they are this, and these are the 4 roots, and this is going to be omega of c. So they could actually convert this into an expression which gives us the location of the roots, and it is omega c exponential j pi by 2 plus pi over 2n plus k pi over n, where k is equal to 0, 1, 2, 2 and minus 1. Okay, so he could actually able to convert this expression into 2n roots which are placed on not on a unit circle but a circle of radius omega of c, 2n of these, and this is your S domain. This is sigma, this is j omega, very symmetrically placed. Now it becomes very interesting and simple. Half I need to give to h of s and the other half I need to give it to. So once you have this, half of the roots you give to h of s and rest of the half you give to h of minus s, as they are symmetrically placed. And we know that left hand side as plane means a stable system and right hand side of s plane means an unstable system. So you give left hand side as plane roots to h of s. And once you have these roots, so h of s becomes a very simple expression. It is s minus your pole 1, s minus your pole 2, and similarly. And the denominator, this omega c, would appear as omega c raised to the power n. So this becomes your transfer function. Done, bingo, he solved the problem. Okay, so he solved a very complex problem of converting something like this into a transfer function like this. And how he solved it? By first constraining it to a monotonically decreasing function of omega, writing its mathematical expression, converting hc of j omega square into h of s and h of minus s, and then taking h of s and minus h of s, h of s and minus h of s, and then splitting this into 2n factors. And how? By finding out its roots, splitting it into 2n factors, finding out the roots, and assigning left hand side as plane to h of s and throwing the rest of it away as h of minus s, and he has a transfer function. Wow. Okay, so this is very, very interesting. We can I think we can take a 5 minutes break, and once I come back I'll also show you some of the, and still we need to figure out how to find out these coefficients. So let us take a 5 minutes break and we come back and start from here again.